Alright, let's do a quick recap of what we did in the last video. We had this linear programming problem to maximize this objective function subject to these constraints, 4 constraints. So what we did was we graphed it. We found a feasible region which looked like this. We used theorem 1 to conclude that the optimum solution must be one of the 4 corner points. We evaluated the optimization function at the 4 corner points, and we just chose the best point. So we can generalize this method to other problems. First, find the feasible region and determine its corner points. Second, evaluate the objective function at each corner point. And big M and little m are the largest and smallest values. When the feasible region is bounded, big M and little m are the maximum and minimum values of Z. And if the feasible region is unbounded, then we have to make some more decisions. Here it tells us what to do, and we'll see why this is in some future examples. That big M will be the maximum value of the objective function if the open half plane determined by ax plus by greater than m has no point in common with the feasible region. If that's true, then big M is the maximum value of Z. Otherwise, Z has no maximum value. Now this may seem a little opaque, but we'll see why this is true in some examples shortly. For minimum, the condition is similar. Little m is the minimum value of the objective function if the open half plane determined by ax plus by is less than little m has no point in common with the feasible region. Otherwise, big Z has no minimum value. So we may consider some examples. Alright, example 1. Solve the following linear programming problem graphically. Maximize this objective function subject to these constraints. Alright, in this case, to graph these constraints is rather straightforward. We have the x greater than or equal to 0, y greater than or equal to 0, so we're always having the positive quadrant. If we use the intercept method I mentioned to you before, for this constraint the x-intercept is 50, the y-intercept is 50. For this constraint the x-intercept is 30, and the y-intercept is 90. And then you'd have to check whether or not 0 is in the regions or not. In this case, 0, 0 is in the region, 0, 0 is in the region. So we get this result here. 4 corner points. Evaluate Z at each of the 4 corner points. Z is given by this function. Find the biggest one, and you're done. Of course, you need to check that the region is bounded, which it is, you can see by inspection. Alright, here's another example. I don't see any particular reason why to go through this. Very similar conditions. You just need to be careful about finding the region. In this case, the point 0, 0 is not a corner point of the region. That's just how it happens to work out. There's no particular reason why 0, 0 always has to be a corner point. Alright, now let's spend a little more time with this one. Here we have optimization function, z equals 3x plus 9y. And here we have 5 constraints. So we have to plot 3 constraints plus the positive quadrant. Alright. And those constraints are 1, 2, 3, like this. Alright. Again, we can plot this using x and y intercepts. This one, x less than or equal to y, you know x equals y is the 45-degree line. So x less than or equal to y, that means x has to be below the 45-degree line. I'm sorry, I got that wrong. If x is less than y, then you need to be to the left. You can check that. Say, for instance, if x is less than y, then that means that 0, 1 should be in the region. 0, 1 is on the upper side of this x equals y. So anyway, you get these three lines intersecting with the x and y axes. You get this blue region. Same deal. No difference there really conceptually. But wait, let me backtrack for a second. One thing that happens in this case is that two of the corner points, two of the vertices have the same value of the objective function, 180, 180. So the two corner points that have the same value of the objective function are C and D. Now it turns out if these 2 points have the same value, then every point on the segment between them also has the same value of the objective function. So in fact, there's not just one optimal solution, there's a whole line segment of optimal solutions. And that's always going to be the case. Either you have a unique solution or you have an infinite number of solutions. If you have two corner points that are solutions, then any point between those two corner points is also an optimal solution. Now, why is it that in this case we have more than one optimal solution? Well, let's look at this problem again. Here we have z equals 3x plus 9y. Okay, so 3x plus 9y, I could write that also as 3 times x plus 3y. Right. Now notice that one of the constraints is x plus 3y. In fact, this objective function and this constraint are parallel lines. Okay. So that means that as I vary z, I can find a value of z that duplicates this constraint. Right? So this is 3 times x plus 3y. This says x plus 3y is less than or equal to 60. So if I make z equal to 180, then what do I get? I get 180 equals 3 times x plus y, or x plus 3y equals 60. It's the same thing. The constraint and the objective function are the same expression. So what does that mean? That means that any point on this constraint will have the same value of the objective function. Now what you can notice here is if you want to find out, to understand what's happening to the objective function, I could plot this function for different values of z. It turns out that this line is the value for z equals 180. Now I could also plot it for a different value. If I plotted it for z equals 0, that would be down here. It would be a parallel line, parallel to this line here, but just has a different intercept. As I vary z, these lines where z is a constant will vary through the region. If I wanted z equal 360, that would be somewhere up here. Now notice something. Z equals 360 does not intersect the feasible region. What does that mean? That means it's not possible to obtain z equal 360 for the possible x and y's that I'm allowed. It is possible to get z equal 180 if I'm on this boundary. Any point in the blue will have z less than 180 because it must be on a line z equals something. Maybe this is z equals 300. And this value is less than the, I'm sorry, it couldn't be 300. It would have to be maybe 160. Sorry, got that wrong. If this is z equal 180, this would have to be a smaller value, maybe z equal 160. all the z-values are smaller than the z-value here. Now this helps to understand why the solution is optimal at a corner point, because the objective function corresponds to a family of parallel lines. I can illustrate what I just said in an example. This is one of the examples he did earlier in the text with my feasible region, and the objective function was z is 4x plus y. Now, if you think about this, as z changes, the intercept of this expression will change, but the slope is always constant. You can work this out if you put this in the form y equals mx plus b. This is the same as y equals minus 4x plus z, and the slope is always equal to minus 4. Right? So if I was going to draw the objective function for different values of z, z equals 0 would be a line something like this. It would go through the origin. Okay. Z equals 30 would have a y-intercept of 30, so here's z equals 30. Z equal 40 would go through the point 40 here, z equal 40, and keep on going, keep on going. Now what happens with these parallel lines? Eventually the parallel line will leave the region. For instance, for z equal, looks like for z equal 100, or let's say for z equal 200, something like that. Certainly for z equal 200, this line is outside of the region. Now you want to find the largest value of z which intersects the region. So you want to find the largest z that intersects the region. And if you think about it, as you pass parallel lines, you could do this with a paper cutout and a ruler. As you pass parallel lines across the region, the last point where the parallel line will intercept this polygonal region will always be at a corner point, because the corner point sticks out. In this case, it looks like B is the corner point. It's going to be the last corner point that intersects these parallel lines. I didn't draw very well. In fact, in this case, it was this point. I think the lines are steeper. But in any case, if you have this family of parallel lines, then the family of parallel lines, the last of the family that intersects the region, is going to intersect at a corner point. So I can summarize this discussion by saying that the objective function corresponds to a family of parallel lines. Okay. And I can say it's the last parallel line determines the optimal value. All right, it's the parallel line, the last one that I can make so it still intercepts the region, is going to give me my optimal value. Now that might not have been quite as clear as I would have liked, but we'll talk about this point further. It's an important point we'll see again and again in this subject. All right, let's go on to another example where we have an objective function here, z equal minus 50x plus 20y. This one has a positive slope. I guess it's going to have slope 5/2. You can work it out. And then here we have different constraints. And if we graph this constraints, it turns out that the feasible region is this blue area, which is unbounded. Okay. Now we have corner points, 1, 2, 3, 4 corner points, but we can't tell whether one of those corner points is the optimal value because the region is unbounded. Now the criterion that they gave you back here was if the region is unbounded, then the value at the smallest corner point is going to be the minimum value only if this line, ax plus by less than m, has no point in common with the feasible region. Now here we're getting back to what I was talking about, that the objective function represents a family of parallel lines. In fact, this condition expresses the fact that ax plus by equals m is the very last of this family of lines that intersects the feasible region. Let's see how that works out in this particular case. All right, in this particular case, as I mentioned, the blue gives me the feasible region, and my objective function is z equals minus 50x plus 20y. Now, of the 4 corner points, this had the smallest value. So we want to know if that's the optimum. Well, this corresponds to minus 300 equals minus 50x plus 20y. Right? So this corner point here corresponds to minus 300 equals minus 50x plus 20y. Now I can divide by 10 and I'll get minus 30 is equal to minus 5x plus 2y. That's a little bit easier to plot. Now if I plot this line, this is what I get. Now what this means is that any point on this line has the same value of objective function. If I take any x and y here and evaluate minus 5x plus 2y, I get minus 30. So if I take minus 50x plus 20y, I'll get minus 300. So if this were the optimal value, then all of these would also be the optimal value, because the objective function is the same everywhere here. All right? But notice that I can move this line a little bit to the right, or not just a little bit, but I can keep moving this line to the right, and the line still intersects my blue region. It still intersects. What does that mean? Any point on this point here, on this line here, that's parallel to this constraint will have the same value of objective function. And the objective function will be smaller, because as I move this way, my z is getting smaller and smaller. So I can find a point in the feasible region that has a smaller value of objective function than minus 300. So minus 300 is not the minimum value. In this case of this unbounded region, there is no minimum value. There's no solution to the minimization problem. And you can read this discussion here. It's saying basically the same thing in different words. All right, here we have another case. Minimize z equals 3x plus 2y with these constraints, and you can graph this. And the feasible region is, well, what is the feasible region? X plus 2y greater than or equal to 8 is this region above the line x plus y equals 8, so it's up here. 3x plus 5y less than or equal to 15 is the dark blue region below this line here. We also know that we have to be in the first quadrant. So in fact, there's no point x and y that satisfies all of these constraints. So the feasible region is empty. There's definitely going to be no solution. All right, so here we summarize 2 points we said before. The feasible region is always a convex region. The empty set is convex because it has no exterior angles. And the maximum or minimum must always occur at a vertex point or a corner point. And if 2 points have the same value of the objective function, then every point on the segment joining those 2 points will have the same value. Okay, so we'll stop there.